Greetings, ladies and gentlemen. I welcome you all to our today's lecture. And basically, we shall talk about subspaces. So, to talk about a subspace, we shall first of all let V to be our vector space over a given field F. Then, if you have a non-empty subset, for example, W, of this set V, so W is a subspace, is a subset of V, which V is a vector space defined over the field F. Then we shall be able to call this non-empty subset W as a subspace of V if W is a vector space under the operations of addition and scalar multiplication defined in V. So to talk about this definition here, if you have a vector space V and you have a non-empty subset, then we shall be able to call this non-empty subset, which is W, as a subspace of V when this W satisfies two conditions, that is, of addition and scalar multiplication, that are already defined for V. Because V is a vector space, it means two conditions are already satisfied. That is, there is vector addition, and scalar multiplication. You know, by the time you define a vector space, then you need to define its vector addition and scalar multiplication. You need to look at what is the addition of any two vectors within that given set. And again, how do I deal with the scalar multiplication of any scalar and a vector from the same set? So you will have addition and scalar multiplication defined. So if you are able to define or to use these same operations, and you show that W here is a vector space on its own using these two operations here, then W qualifies to be called a subspace. So here we are saying the way in which one shows that any set W is a vector space is to show that W satisfies 8 axioms of a vector space. However, because W is already a subset of a vector space, V, then it means some of the axioms automatically hold in W because W is already a subset of this vector space V. So which means that some axioms will automatically hold. So because of that, in order to identify or in order to show that W is a subspace, you only need to prove only two conditions, that is for vector addition and scalar multiplication. If they satisfy, then we shall basically say that W is a subspace of vector space V. So I hope the definition is very clear. Now, how do you test for a subspace? So clearly we have already said if W is a non-empty subset of vector space V, then this W will be called a subspace if two of the following conditions hold. So we have only two conditions that we shall always try to prove. If they hold, then we shall call that given non-empty subset as a subspace. So these two are: one, the zero vector, that is 0, must belong to W, which means the zero vector must belong to that given non-empty subset. So why do we do this? One, we need to show that W is not empty, because when we look at some of the conditions that we need or when you look at the definition, one, you must consider a non-empty subset. So one, in order to show that W is not empty, then you must show that there is a zero vector in that W. Two, to talk about scalar multiplication and vector addition. Two, when you pick any two vectors from W, for example, U and V, if you pick U and V from this given set W, and maybe you have C as your scalar from the scalar field F, then the vector addition, that is U plus V, must be in W, and at the same time, if you have C and N vectors from W, then C and W, that is for scalar multiplication, this one should also be in W. So it should hold for vector addition and scalar multiplication. We have so far seen how to test for a subspace, that these two conditions must be satisfied, that is a zero vector must belong to W, and also if U and V are picked from W, then the vector addition and scalar multiplication must hold in W. So these two properties here, this one here implies that W this property here implies that W is closed. W is closed under vector addition, and when we talk about this one here, this property implies that W is closed under scalar multiplication. So, meaning that to look at a subspace, you must show that W is closed under vector addition and scalar multiplication. And don't forget that you must as well show that the zero vector belongs to W. But also, having these two conditions here, you can still, that is B1 and 2, you can still combine the two. Combining the two, and you form one and you form one condition out of these two. For example, if you have U and V as elements of W, you also pick any scalars, maybe A and B, from the scalar field. So instead of proving 1 and 2, you can prove them at once by combining the two. So if I have U and V as elements in W, or vectors in W, then I have two scalars A and B, then I can simply prove this one here, the two conditions at once, by taking the linear combination of the two, that is AU plus BV. So if I prove that this one here is an element or is a vector in W, then I will have combined the two, that is for vector addition and scalar multiplication. So if I show that this combination, that is AU plus BV, if I show that this combination here is also in W, then I will have proved all the two at once. So in other words, I would only show that the zero vector belongs to W, and this one also belongs to W, and if the two satisfy, then I will be able to say that that given an empty subset of a vector space V is actually a subspace. So that is basically what we are talking about in our next slide here. So we are saying property 1 in B states that W is closed under vector addition, and property 2 states that W is closed under scalar multiplication. So however, both properties may be combined into an equivalent single statement. So if you want to combine these two properties here into a single statement, then you will do like the way we have done here. That is, you pick any two vectors from W and you show that this linear combination of AU plus BV is also in W. So let us also talk about some of what we call the trivial or obvious subspaces. We have got two obvious subspaces for any given vector space. For example, if you consider V to be your vector space over the field F, then V contains automatically two subspaces. One, we have the set 0. This set here, which is containing the 0 vector alone, is always a subspace of any given vector space. In other words, a 0 vector satisfies the two conditions that we have seen above. So this is a vector that is consisting of a 0 vector alone, and the whole space V itself is also what we call a subspace. So these subspaces here, that is the set 0, that is the set that is consisting of a 0 vector, and the whole space V, that is the set itself. They are sometimes called the trivial subspaces. In other words, they are obvious ones. They will always be there. So these are the trivial subspaces that we shall always be having. And for that case, in case you are asked to give any two subspaces that are trivial or the obvious subspaces, we shall always be having the set consisting of a 0 and the whole space V, or the set itself. So these are the trivial subspaces. But then we shall look at some examples of some of the subspaces which are actually not trivial subspaces. So let us come to examples. Let us now talk about some examples pertaining subspaces. We are given the set S, which set S satisfies the condition that for any x, y, z picked from R3, then x plus y minus z must be equal to 0. So we need to show that S is a subspace of R3. So we shall try to solve that one together. So let us have the set. We are given the set S, which set S satisfies the condition that when you pick any x, y, and z from R3, then when you get x plus y minus z, this must give you 0. So you need to show that S is a subspace of R3. You need to show that S is a subspace of R3. But as we said, to show that a given set is a subspace, show that a given subset of a given vector space is a subspace, you must prove 3 conditions. 1, you must show that a 0 vector exists within this set that you are considering. So let us get back some of these conditions that we need. 1, we must show that the 0 vector belongs to W. Let us try to show that a 0 vector belongs to W. Let us let 0 to represent the 0 vector in this set here. So if we pick the 0 vector from R3, the 0 vector from R3 is the vector which is 0, 0, 0. So this is the 0 vector from R3. So however, when we look at this one here, 0 equaling to 0, 0, 0, that is in position for x, y, and z. So when you have this one here, if I have 0 plus 0 minus 0, what do I get? I will get a 0. In other words, you can easily see this represents the x component, the y component, and this represents the z component. So when you get a 0 plus 0 minus 0, completely you will get a 0. And if this one holds, then clearly it means this as well holds. Because you have got x component which is 0 plus y component which is 0 minus z component which is 0. And when you do this, you are getting a 0, which means that this 0 that we are talking about, which is equaling to this, is actually an element from this given set. Therefore, this will imply that 0 is actually an element of S, because 0 is satisfying the condition which is satisfied by any x, y, and z picked from R3, which means this condition must be satisfied. And we have seen that 0, 0, 0 plus 0 minus 0 will give you 0, which means this condition is satisfied, and for that case, any vector that satisfies this condition is an element of S. So clearly, the 0 vector is an element of S. So here you have already shown that S is actually non-empty. That is what you have shown. 2. We must as well show that for every vector u v picked from W and scalar picked from the scalar field, then the 2 must as well be satisfied. So let us look at the one for closure and addition. So we shall say condition number 2, we shall need to show that is S. We need to show that is S closed under vector addition. Is S closed under vector addition? Is S closed under vector addition? This is what we need to prove. So to prove that, we must let any two vectors, that is let, for example, P, vector P, be of the form. Remember, we are picking X, Y, and Z from R3. So it will be of the form A, B, and C, for example. Then we shall need to pick 2. That is also, we can pick Q, which is maybe D, E, and F. Remember, P and Q, these elements A, B, and C should be elements from R3. So that's why they are of this form. So B elements from S. If P and Q are elements from S, this one here implies we are saying P and Q are elements from S, but P is this and Q is this. First of all, if P is an element of S, by this condition, it means P satisfies this given condition. So this will imply that X component is A, that is A, plus Y component is B, minus C is equal to 0. We are writing this because we are saying P is an element of S. If P is an element of S, then its components, that is for X, Y, and Z, must satisfy this given condition. Similarly, Q, which is having entries D, E, and F, is also an element of S. If that is true, it also implies that when you get D plus E minus F, you also get a 0. So this is by definition that for any given vectors we pick from S, this condition must be satisfied. And if we pick P and Q from S, then it means they satisfy this. So now, what is our interest? Our interest, looking at what we need here, we need to show that U plus V is also an element of W. So we need to show that P plus Q is also an element of S. So we shall write. So we need to show, according to what, to show that S is closed under vector addition, we need to show that P plus Q is an element of S. This is what we are looking at. So this is what basically we want to show. But we have already got P and Q. So let us look at what is P plus Q. P plus Q is same as getting A, B, and C. You add there D, E, and F. Remember, P is this, Q is this. So what will this give us? This is same as when we are adding these two vectors, then we add the corresponding components, A plus D, B plus E, then C plus F. So that is what we have so far. But we need to show that P plus Q is an element of S. And if that is to be true, then its X component, Y component minus Z component, you should be able to get a 0. So let us look at, we have got P plus Q as this. So we have P plus Q as A plus, as A plus D, B plus E, C plus F. This is what we have. Now let us look at this condition that must be satisfied. The condition that must be satisfied is when you get the X component plus Y component minus Z component, you must get a 0. Okay, so let us look at that. What is the X component of this? This is the Y component and this is the Z component. So when I get A plus D, X component, I add there B minus B plus E, Y component, then I subtract there C plus F, I should be able to get a 0. That is what we need to show. Because by definition, when you get X component plus Y component minus Z component, you must get a 0. So for that case, when I get A plus D plus B plus E minus this, I want to show that this one here is equal to 0. This is what I want to show. I want to show that A plus D plus B plus E minus C plus F, I get a what? I get a 0. This is what I need to show. Because this is in position for X, Y, and this is position for Z. So let us look at this and see whether it will give us a 0. So looking at this, we shall say, let us try to add A plus D plus B plus E, or when I open this bracket, minus C minus F. When I look at this, remember that when we were starting here, we already defined that P and Q are elements of S, and A plus B minus C is equal to 0, D plus E minus F is equal to 0. So I can use these ones here, because when I look at what I have here, you realize that A, I can easily get A plus this B minus this C. So I can easily combine this, then plus I can also easily combine D with E minus F. But what is this one equaling to and what is this one equaling to? We have already defined that A plus B minus C is equal to 0 and D plus E minus F is equal to 0 by the fact that P and Q are elements of S. So in other words, here I can put 0, then this one is also 0. So what will this one give? It will give us 0. So clearly, A plus D plus B plus E minus C plus F is giving us 0, which I wanted to prove. So if I have proved that one, then I will come to this. A plus D, B plus E minus this. What are these components for? These are components of P plus Q. And we can easily see that P plus Q, whose components are A plus D, B plus E, C plus F, are satisfying the condition for any given vectors in set S. and that one therefore implies that P plus Q is actually an element of S, because P plus Q is satisfying the condition for the vectors that are picked from S. So this clearly implies that S is closed, under vector addition. S is closed under vector addition. So now we look at the next condition that must be satisfied. Remember, there are three conditions: the one for the zero vector, and the one for the closed under vector addition, and the next should be closed under scalar multiplication. So let us look at condition number 3. We need to show that S is closed under scalar multiplication. And how do you prove that? If you have any scalar from the scalar field, then you pick any vector, for example P from S, then you must show that alpha P is an element from S. Now, we shall let, in order to prove this, we shall let P be an element of S. If P becomes an element of S, then let P be in form of A, B, and C. Let P be an element of S, which P is of this form. What will this one imply? By definition of any vector from S, it should satisfy the condition that x plus y minus z is equal to 0. But for our case, our x is A, our y is B, our z is C. So in other words, A plus B minus C should be equal to 0. So since P is an element of S already, then this condition is satisfied. Now, also, we shall consider an alpha from the scalar field F. Let us talk about what we need to prove. We need to show that alpha times P is an element of S. But what is alpha P? Alpha P same as alpha into what is P? P is A, B, and C. What is this one equaling to? This is same as alpha of A, alpha of B, and alpha of C. This is alpha P. So next, we need to show that this alpha P is an element of S. But alpha P is same as this one here. So alpha P has got, in X coordinate we have alpha A, Y coordinate we have alpha B, Z coordinate we have alpha C. So what do we need to prove? We need to show that when you get X coordinate, which is alpha A, you add there Y coordinate, which is alpha B, you subtract there, by definition, the Z component, which is alpha S, you must get what? You must get a 0. This is what we need to prove. So let us first of all consider alpha A plus alpha B minus alpha C from the definition for any elements in S or any vectors in S must satisfy this given condition. So, but we need to prove that this one is equal to 0. So this one is equal to, we need to show that this is equal to 0. So if I have alpha A plus alpha B minus alpha C, when I substitute for X, Y, and Z coordinates in the condition given, then what will I have? This is same as having alpha into A plus B minus C. That is when I pull out this alpha, because it's a common factor. So this will give us alpha. Do I have this? I have already said that a plus b minus c is equal to 0. So this is times 0. So alpha times 0 is actually what? 0. So clearly we have alpha a plus alpha b minus alpha c equaling to 0. So if this is true, clearly we have proved that this one holds. But what is alpha a, alpha b minus alpha c? This is the x coordinate for alpha p, y coordinate for alpha p, z coordinate for alpha p. But we have seen that when you add the x component, y component minus z component, you actually get a 0. So when that one happens, then clearly by our definition, that this condition must hold, then we shall say that that given element or that given vector is from that set S. So now it is clear that this one here holds. For that case, this one will imply that alpha p is an element of S. Because these are components for alpha p, so you should be able to conclude if this one happens. So alpha p is an element of S. Therefore S is closed. Therefore S is closed under scalar multiplication. Is closed under scalar multiplication. So we have proved all the three conditions, and for that case, we should be able to give the conclusion that S is actually a subspace of R3. So having proved all the three conditions, we shall therefore say clearly S is a subspace. Clearly, S is a subspace of R3. And that will be the proof. We now look at example number 2. Example number 2 says, let S be equal to, we have X, Y, and Z picked from R3, for which these components here, X, Y, and Z, satisfy this given condition. That is, X plus Y plus Z is equal to 3. Meaning that for any vector that is picked from S, it must satisfy this given condition that the X component plus Y component plus Z component must give you a 3. So let us show whether S is a subspace or not. We shall look at the solution. So to look at the solution, we need to prove three things. One, you must show that a zero vector exists. We must show that the zero vector exists in S. So part 1, we show that a zero vector is an element of S. In other words, we want to show that S is not empty. So let us look at how best we can show that. Since we want to consider a zero vector, let 0 to be of the form 0, 0, and 0. That is for X component, which is 0, Y component, which is 0, Z component, which is 0. By definition, I will write our set here. Our set is set S, for which we have X, Y, and Z from R3, but X plus Y plus Z is equal to 3. So when we look at this, we have 0 equaling to 0, 0, 0. That's why we are rating this. We are picking any component which is from R3, that is 0, 0, 0. So it must be of the form X, Y, and Z. So if we pick or we let 0 to be equaling to this is our 0 vector, then we know that when we get 0 plus 0, when we get x component plus y component plus z component, we shall get a what? 0 plus 0 plus 0 gives us 0. So clearly, you can see that this 0 is actually not equal to what? Not equal to 3, because when you add x, y, and z component, if it belongs to S, it should satisfy this component, which is x plus y plus z equaling to 3. So for our case, our x is 0, y is 0, z is 0. But we realize that when you get 0 plus 0 plus 0, you get 0, which is not equal to 3. So if that one happens, we clearly say that this 0 is not an element of S. Because if 0 is an element of S, we would get 0 plus 0 plus 0 equaling to 3. So which is not being satisfied. So a 0 vector is not an element of S. That is part 1. Part 2, we need to show that S is closed under vector addition. We need to show that S is closed. We need to show that S is closed under vector addition. Is closed under vector addition. To show that S is closed under vector addition, you must pick two vectors from S and you show that their addition is also in S. So we shall let P and Q to be vectors in S. If we let P and Q to be vectors in S, we shall also let P to be of the form A, B, and C. Then we shall also let Q to be of the form D, E, and F. So, what do we need to show? Here, what we need to show is we need to show that P plus Q is also an element of S. This is what we need to show. So we have already let our two vectors P and Q to be from S, but P is of this form and Q is of this form. So by the fact that P and Q are elements of S, then they satisfy this given condition. So let us say this implies, since P and Q, we are saying since P and Q are elements from S, it will imply that P and Q satisfy this given condition of S, because P and Q are elements from S, which means their components satisfy this given condition. So what is P? P is A, B, and C, meaning that A plus B plus C, X component, Y component, Z component gives you S3. Also, since Q is also an element of S and Q is this, then it means D plus E plus F is also equal to 3. So we are doing this because we have already said P and Q are elements of S. If they are elements of S, they satisfy this given condition. So let us have that one. So for example, that is our equation star. But our interest is to show that P plus Q is an element of S. If that is the case, we need to first of all know what is P plus Q. So P plus Q is same as getting A, B, and C. You add there, Q is D, E, and F. When you do that, what will be the corresponding components? We shall have A plus D, A plus D, B plus E, then C plus F. This is what we have. So we must show that this one here, if we want to show that P plus Q is an element of S, we must show that when we get A plus D, B plus E, C plus F will give us a 3. Okay, so what are we interested in after we have seen this? So to show that, let us put it here, to show that P plus Q is an element of S. If you want to show this, then you must show that A plus D, you must show that A plus D plus B plus E plus C plus F, you must show that when you add these components by this fact here, you must be able to get a 3. It must satisfy this condition for P plus Q to be an element of S. So this is what we need to show. So this is what we need to show. So in order to show that P plus Q is an element of S, you must show that the components for P plus Q will satisfy this given condition. So let us try to consider that one. That is what we are interested in. So we have seen that P plus Q is same as A plus D, B plus E, C plus F. This is what we have as our P plus Q. A plus D, B plus E, C plus F. So if that is what we have, remember we need to show that P plus Q is an element of S, and for that case we need to show that A plus D, B plus E, C plus F is equal to 3. So since we need to show this, then let us begin with the left hand side. So we shall consider the left hand side. We need to consider what will be A plus D plus B plus E plus C plus F. We need to consider this. So we need to show that this one is equal to 3. If it does not, then it means P plus Q does not belong to S. So A plus D is the X component, this is the Y component, this is the Z component of P plus Q. So A plus D is the X component. So in other words, we are getting X plus Y plus Z. So we want to see whether it will give us a 3. So here, since we are adding, these are real numbers, so we can consider A plus D plus B plus E plus C plus F. We can consider these components. So since from what we already have A plus B plus E equaling to 3, D plus E plus F equaling to 3 also, let us try to create A plus B plus C, D plus E plus F, since we already have that in equation star. So we can say the A, we can add there B, we can add there C. This is possible since we are dealing with real numbers. This is D plus C. This is D plus E, then plus F, B plus D plus F. When you look at this from equation star, from this equation here, A plus B plus C is 3, D plus E plus F is 3. So it means this is same as 3, this is also same as 3. This is from equation star. This is from equation star. So which will give us a 6, because 3 plus 3 will be 6. So A plus D plus B plus E plus C plus F is giving us 6. But this 6 here is not equal to 3, because we are seeing we wanted to show that P plus Q is an element in S, and this one must give us a 3. But instead, this expression is giving us 6, which is not equal to 3. So clearly, this implies that these components for P plus Q implies that they don't satisfy the condition that X plus Y plus Z is equal to 3. Instead, they are satisfying is equal to 6, where 3 is not equal to 6. So if that is the case, then we conclude that P plus Q is a vector which is actually not belonging to S. So P plus Q does not belong to S. So far we have seen that 0 does not belong to S, P plus 2 does not belong to S. So clearly we should be having a clear picture that this set here, which is set S, is actually not a subspace of R3, because we want to show that S is a subspace of R3. So far, no condition is satisfied, because 0 vector does not belong to S, and also P plus 2 does not belong to S. So clearly, we should be having a clear picture that S is actually not a subspace of R3. But let us look at the last condition, which is a closure under scalar multiplication, and see whether it will also satisfy. So condition number 3, we need to show that S is closed. We need to show that S is closed under scalar multiplication. So in order to show that S is closed under scalar multiplication, what do we need? We need a vector from S. We need a vector from S, for example P, to be an element of S. We also need alpha to be a scalar, such that if P is an element from S, we shall let P to be of the form A, B, and C. That is of the form X, Y, and Z, because it must have the X component, Y component, and Z component for us to apply our given condition. Remember that S is when you have X, Y, and Z, which are elements of R3, then X plus Y plus Z, this gives us a 3. This is the condition for any vectors picked from S that must be satisfied. So we have let our P to be an element from S. We have our alpha from F. Then P is of this form. What is our interest? We need to show. If we need to show this, then instead we want to show that alpha P is an element of S. This is our main interest. This one here is our main interest. We want to show that alpha P is an element of S. So let us look at this one here. We have said that since P is an element of S, clearly it implies A plus B plus C will give us a 3. We have said let P be an element of S. So by definition, then A, B, and C, their components added must give you a 3. This is the fact because P is an element of S. Now, let us talk about alpha P. So what about alpha P? What is alpha P? So for alpha P, what is alpha P? Alpha P is same as alpha into P. But what is P? P is same as A, B, and C. P is this, not this one here. Don't substitute this. So P is A, B, and C. This one. So this is same as alpha A, alpha B, and alpha C. This is our alpha P. So what we need to show now? We have alpha P as this, but remember we want to show that alpha P is an element of S. And if alpha P is an element of S, so in other words, we want to show, let me put it here so we can know what we want. So we want to show that alpha P is an element of S. So in other words, we want to show that when we get alpha A plus alpha B plus alpha C, we shall get a 3. This is what we are interested in. If we show this one here, because by the condition given that X plus Y plus Z must give us a 3, if alpha P is an element of S, then when you get alpha A plus alpha B plus alpha C, you must get a 3. So this is what we want. So if this is what we want, let us consider the left hand side. So let us consider the left hand side, which is alpha A plus alpha B plus alpha C. What will this one be equaling to? So we are considering the x component plus y component plus z component. We want to see whether it will give us a 3. So when you get alpha A plus alpha B plus alpha C, so we can say alpha is common, so we can pull alpha out, we remain with alpha into A plus B plus C. So, but this is same as alpha times, we already have this because we already have that A plus B plus C. For example, this is our equation star. When we get A plus B plus C, we get a 3 because P is, we have let P to be an element of S. So alpha times A plus B plus C is a 3. So this will give us 3 alpha. This is from the from equation star. So we are getting alpha A plus alpha B plus alpha C equaling to 3 alpha. What does that one imply? Remember, for us we wanted to show that alpha A plus alpha B plus alpha C is equal to 3. But instead we are getting 3 alpha. Okay? So when you get 3 alpha, what does that one mean? Remember, alpha is a real number. So since alpha is a real number, it means this expression will not hold for all the values of alpha. Because if, for example, if alpha is, for example, 1, if alpha is, for example, 1, this statement will hold because we shall have alpha A plus alpha B plus alpha C equaling to 3 times 1. In other words, you will have 1 times A plus 1 times B plus 1 times C equaling to 3 times 1, which is true because this one will hold, which will satisfy this given condition. But look at the case when alpha is not equal to 1. If alpha is not equal to 1, for example, if alpha is 0, you will get alpha A plus alpha B plus alpha C equaling to 0, which will not hold for this given condition. If alpha is, for example, 2, you will have 2 alpha or alpha A plus alpha B plus alpha C equaling to 6, which will not hold true for this given condition. So from here we shall give a conclusion. We shall give a conclusion that alpha A plus alpha B plus alpha C, this one here, which is equal to 3 alpha, will be equaling to 3 alpha, we shall say this one here will be equaling to 3 alpha, which is not equal to 3. This one here, this 3 alpha is not equal to 3. Remember, our interest was to show that alpha A plus alpha B plus alpha C is equal to 3. But alpha A plus alpha B plus alpha C is equal to 3 alpha. So this 3 alpha is not equal to 3. And this happens for all alpha not equal to 1. So if alpha is not equal to 1, then this expression will not hold because this will no longer be a 3. But if alpha is equal to 1, it can hold. But we are looking at for all values of alpha, it will not hold true, which means that this statement here holds for only when alpha is equal to 1. But otherwise, it will not hold. So alpha A plus alpha B plus alpha C will be equal to 3 alpha, but this will not be equal to 3 for all values of alpha not equal to 1. And what does that one mean? That one means
That one means that actually alpha p is not an element of S because it does not satisfy this given condition for all values of alpha. So clearly these components alpha A, alpha B and alpha C are components of alpha P. So since they are components of alpha P and they don't satisfy this given condition, then we shall conclude that alpha P is not an element of S. So looking at the three conditions, condition 1, 2, and now condition 3, all these conditions are not satisfying. And if that is the case, you should be able to put your conclusion that therefore, since S does not satisfy all the conditions, therefore, since S does not satisfy all the conditions, for a subspace. Therefore, since S does not satisfy all the conditions, for a subspace, then clearly S is not a subspace. S is not a subspace of R3. In our example number 3, we are given V, where we have x1, x2, x3 picked from R3, for which these components, that is x1, x2, x3, satisfy the condition that x3, that is this component, is equal to x1 plus x2. So we need to show whether V is a subspace of R3. So to do that, we shall follow the same method or the same way we have been proving our previous examples. So let us look at the solution. We are given V, which is having the components x1, x2, x3 satisfying the condition that x3 is same as x1 plus x2. So we need to show whether V is a subspace or not. Now, we begin with the first condition. The first condition, we need to show that a zero vector, is an element of this set V. So that is, in other words, you need to show that V is actually not empty. So in order to show this, we shall begin with a zero vector. Let a zero vector be of the form, we are given the form x1, x2, and x3. Let us consider 0, 0, 0. So this is a zero vector, but since we are dealing with x1, x2, and x3 from R3, so our 0 will also have 3 components. So now, let us talk about, if I get a 0, can I say 0 is same as 0 plus 0? This is true because when I consider x component to be 0, then this is the x3 component 0, then x1 is 0, x2 is also 0. So clearly I can say 0 is same as 0 plus 0, and if this one holds, it means this expression holds also. So if this expression holds, then clearly we can say that 0 is an element of V because it holds true. When you get 0, which is the x3 component, it will be equal to 0 plus 0. Because 0 equaling to 0 plus 0, the statement is true. Now, let us talk about the second condition. In our second condition, what do we need? We need to show that V is closed under vector addition. V is closed under vector addition. V is closed under vector addition. So V to be closed under vector addition, you need to pick any two vectors in V, then you show that the sum is also in V. So let us consider two vectors from V. For example, P, let P and Q be elements from V. Okay, where P is of the form A, B, and C. Then Q is of the form D, E, and F. So since P and Q are elements from V, it means they satisfy this given condition. So we shall say, since P and Q belong to V, then it implies P and Q satisfy this given condition, that their x3 component is same as x1 component plus x2 component. So what is the x3 component? According to this, x3 component is C. So C is the same as A plus B. C is same as A plus B. This is like your x1, this is like your x2, this is like your x3. So C is same as x1, which is A plus B. Also, if Q is an element of V, then also F, which is the x3 component. This is like your x1, x2, x3. So F is also same as x1, which is D, plus x2, which is E. So C is same as A plus B, F is same as D plus E. We can let this to be equation star. So that is for the condition that P and Q are elements from V, meaning they must satisfy this given condition. Now let us talk about P plus Q. Remember, our interest is when you pick P and Q from V, then you need to show that P plus Q is also an element in V. This is what we are interested in. So if that is our interest, we shall need to talk about P plus Q. What is P plus Q? P is same as A, B, and C. Q is same as D, E, and F. So this will give us, when you add the corresponding components, you will get A plus D, B plus E, C plus F. This is what we get. So meaning that P plus Q is same as A plus D, B plus E, C plus F. This is what we have as P plus Q. So in order to show that P plus Q is an element of V, what do we need to show? So let me put it here so you can know what we are interested in. So for P plus Q to be an element of V, then it means, so for P plus Q to be an element of V, we must show that A plus D, B plus E, this one here, satisfy the condition for elements from V. Remember, for elements in V, x3 must be equal to x1 plus x2. This is the given condition. So what we need to show is, for P plus Q picked from V, then we must show that A plus D, B plus E, C plus F satisfy this given condition. So what is your x3? x3 is C plus F. So you must show that C plus F is actually equal to A plus D, then A plus D, which is your x1 component, this is your x2 component, this is B plus E. So this is what you must show. For P plus Q as an element of V, for you to show that P plus Q is an element of V, then you must show this. So this is what we are interested in. Okay? Now we already have our P plus Q to be equal to this. So for that case, this is what we need to show. So for that case, we need to consider this left hand side to get the right hand side. So let us consider P plus Q. Let us consider P. We need to consider that to show that P plus Q is an element of V. So let us consider the left hand side here, which is C plus F. So what is C plus F? We need to show that this is equal to this. So let us consider the left hand side, C plus F. So we have already seen that C is A plus B, F is already D plus E. So from equation star, we can easily get C and F. So what is C? C is same as A plus B. What about F? We are picking from here. F is same as C is this. F is D plus E. F is D plus E. This is what we have. So A plus B, D plus E. This is from star. Now, we are interested in this. So I can write this as A plus B plus D plus E, which I can also write as, since we are dealing with real numbers, A plus, I can write this as A plus D, again plus this one and this, B plus E. So when you look at this expression here, C plus F is equal to A plus D plus B plus E. When you look at this, it is what we are interested in. So clearly, it means C plus F is equal to A plus D plus B plus E. So if this one holds, what are these components for? This is x1, this is x2, but this is x3. So in other words, we are getting x3 equaling to x1 plus x2, which means this condition will be satisfied. But C plus F, A plus D, B plus E are the components for P plus Q. If that is the case, therefore we can conclude that P plus Q is actually an element of V. So that condition will hold. Let us look at the last condition. So for the last condition, we need to show, condition number 3, we need to show that V is closed. We need to show that V is closed under scalar multiplication. Under scalar multiplication. And to show that you must pick one element from that given V, that given set. Then you also must consider a scalar. You must also consider a scalar from a given field. So if that one happens, then you will need to show that alpha P is also in V. So let us have our P to be of the form A, B, and C. Now we shall say, since P is an element of V, then it implies P satisfies the given condition that x3 is same as x1 plus x2. But what is your x3 for this case is C. What is your x1 is A. What is your x2 is B. So meaning this one holds. So what is our interest? Our interest, we need to show that if P is an element of V and you have alpha which is a scalar, then you need to show that alpha P is an element of V. This is what we are interested in. So in order to show that, then you must talk about alpha P. What is your alpha P? Your alpha P is same as alpha into P, but P is same as A, B, and C. Don't put this one as your P. This is by the condition that P is an element of V, but we are simply talking about alpha and P. So this will give us alpha A, alpha B, and alpha C. So your alpha P will be same as this. Now, after getting alpha P, what are you interested in? After getting alpha P, you need to show that this alpha A, alpha B, and alpha C satisfy this given condition for alpha P to be an element of V. So you need to show that alpha P is an element which alpha P is a vector which satisfies this. And for this to be satisfied, what is your alpha A, what is your alpha B, what is your alpha C? This is your x1, this is your x2, and this is your x3. So in other words, you need to show that alpha C is same as alpha A plus alpha B. This is what you are interested in. Okay. So in order to show this, let us consider this left hand side. So you will consider the left hand side. What is the left hand side? Is alpha C. And what are you interested in? You want to get alpha C equaling to this. So this is what you need. So you will consider the x3 component, which is this one here. X3 component is alpha C, and see whether you will get alpha C equaling to alpha A plus alpha B. So let us look at this. This is alpha times C, which is same as alpha times what is C? According to what we have already here, C is same as A plus B. C is same as A plus B. So this is same as, this is from equation star. This is from equation star. So what is alpha C? Alpha C is equal to alpha times C, but C from equation star we got it as A plus B. So I can expand this. This is alpha times A plus alpha times B. So clearly this will imply that alpha C is same as alpha A plus alpha B. When you look at this and what you needed to prove, the two are the same. So clearly we can now conclude that since these are components, because this is x3, this is your x1, this is your x2, so these are the components of alpha P. Which components are satisfying this given condition? So therefore, alpha P is an element in V, because elements in V satisfy this condition, and we have seen that alpha P is satisfying the same condition. Therefore, alpha P is an element of V. So if that one happens, we clearly look at the three conditions, 1, 2, and 3. So clearly all the conditions are being satisfied. So if that one happens, then you can now give a conclusion that since V satisfies all the conditions. So which conditions? That is V is closed. Since V is closed under scalar multiplication, those are the conditions. Since V is closed under scalar multiplication and vector addition and vector addition and vector addition, of course, and V is not empty, that is V is non-empty, then clearly, since V satisfies all the conditions, which conditions? V is closed under scalar multiplication and closed under vector addition, and most importantly, V is not empty, then V is a subspace of R3, is a subspace of R3, is a subspace of R3. So that will be the proof. So that is where we shall stop, and we shall be able to add on in our next lecture.
Yeah.